So next presentation title is the effect of hydrogen on the collective behavior of dislocation during nanoindentation. That is given by the Professor He? Sorry. So please start.
Is working? Yes, thank you. Yeah, thank you for the introduction. My name is Jianying He. I'm from Norwegian University of Science and Technology. So I will continue the discussion about hydrogen embrittlement in the small-scale plasticity. So it will be the effect of hydrogen on the dislocation behavior during the indentation process. And different with the previous two speakers, I will actually talk from the perspective of proposed continuum model and the verification by the molecular dynamic simulation. So my co-authors is our former PhD candidate, Kai Zhao, now postdoc at Aarhus University, Denmark, and my senior colleague, Professor Zhiliang Zhang. These days, we have been talking a lot about the hydrogen embrittlement. So this work is mainly based on our publication this year in Acta Materials, and I will follow the outline. First is the background and the motivation. Hydrogen embrittlement in a nutshell. And then it's the proposed continuum model based on the classic expanding cavity model. We introduce the hydrogen into that. And it's the molecular dynamic simulation of the indentation process in hydrogen embrittlement to calibrate and verify the proposed continuum model. And at the end is the conclusion, or hopefully trigger more discussion with you, give us some comments and suggestions. Yeah, many colleagues have talked about the mechanisms of the hydrogen embrittlement. And of course, there are two commonly accepted mechanisms. The hydrogen-enhanced decohesion, in short, HED, and hydrogen-enhanced localized plasticity, HELP. And HED is originated from the short-range lattice dynamics. So the intrinsic length scale determines that the first principle calculation is suitable for study the HED mechanism, and that has been studied a lot. While the HELP considers the long-range stress field, so it requires the exact description of the stress field around a dislocation, and that makes trouble. A lot of work have been done on the interaction of the hydrogen with the single dislocation line, and either screw dislocation or edge dislocation. However, only few work have been done on the collective behavior of the dislocation. So HELP has been observed here and there. Thanks, Afros, for this wonderful talk, introduce this HELP mechanism. And our goal here is try to establish a predictive model to capture the on-the-fly process of the HELP during the nanoindentation, and try to study the HELP with the small-scale plasticity. And our starting point is this expanding cavity model. And this has been proposed a long time ago and widely used to describe the indentation process. And the key message here is that we have a spherical indenter, and we will have a hemispherical plastic zone around this indenter. And that's the key message. It will influence us when introduce the hydrogen into this model. And then, quite recently, Meyer and the co-worker, they proposed the dislocation density-based method to evaluate the void growth through the dislocation generation and the sleeping. And if you read these two, you may find something common. Is there any similarity between this, the ECM described the nanoindentation process and this void growth? Because ECM is actually based on Hill's solution of the internally pressurized spherical shell expansion. So there is a similarity. And can we borrow the method proposed by Meyer and co-workers and introduce the dislocation density into the indentation process. So this is the concept or the ideas that we have to get this continuum model. And now the question is that how to include the hydrogen into the model. Hydrogen is everywhere in the material, and in this model we develop, we assume that hydrogen tends to diffuse to the plastic zone. And that's actually how it happened during the experiment, because the diffusivity of the hydrogen determines that it will try to come to the plastic zone and concentrate at the void surface. Yeah, in the model process, how to realize that? And this is the flow chart we implemented in the MATLAB. So we have here that the expanding cavity model for the indentation, and the stress can be decomposed to two components. The shear component, which determines the dislocation, nucleation, and the motion. And that will contribute finally to the indentation, force, and displacement evolution. And second component is the hydrostatic stress. And we use the process that the chemical potential will drive the hydrogen diffusion in the same manner as Professor Song and Curtin's work. And this will enable us to calibrate the hydrogen-induced solute drag applied to a dislocation, and combine the final resultant of the two stress components together, we'll be able to obtain the ordinary differential equation during the nanoindentation. So that's the force evolution with the time, and the dislocation density evolution with the time. And by numerically solve the two equations, and we'll be able to get the force and displacement curve of the indentation in the hydrogen environment. And here is some more message to emphasize that in this dislocation density evolution, we will have three contributions: the homogeneous nucleation of dislocation, the heterogeneous nucleation of dislocation, and these two have been well included in the nucleation theory. And another is that the dislocation annihilation contribution, and all of them will be influenced actually by the hydrogen. So when hydrogen entered the plastic zone and trapped by dislocation loop, and it will influence the dislocation, the energetics, mobility. So now we have a very the crude continuum model based on the expanding cavity model and involve the hydrogen there. And next that at the same time, we try to run the molecular dynamic simulation to calibrate and verify this continuum model. And our simulation detail is that we have the nickel box around 6 million atoms, and we use the force field that nickel hydrogen EM potential and nickel EM potential to describe the interatomic interactions. And the total length scale is the 40 nanometer cubic, while that the indenter is a spherical shape with the radius 6 nanometer. And the velocity we used is the 0.5 angstrom per picosecond. So it's really high speed compared to the experiment. And the hydrogen amount we put, this is the atomic concentration. So it's the total number of hydrogen atoms that we put in the indentation. And the method we use is also similar to Professor Song and Curtin's work. It's a dispersively distributed hydrogen atom in the box. We have a simple calculation here that if it's 1,000 hydrogen atom, it's corresponding to the number of hydrogen per unit length in the plastic zone around this concentration, 0.0168%. So this is the value we also use as the equilibrium hydrogen concentration in the continuum model. Yeah, let's see some results and how the comparison of the continuum model with the molecular simulation. So this figure gives quite a lot of information. Let's spend some effort on that. First, that we can see that in the elastic region, the molecular simulation result, those fluctuation curves, and the continuum model, they fit quite well with the Hertz elasticity model. But that's only describe a very small elastic string region. And in general, that if we compare the case with or without hydrogen, it's predicted by both the continuum model and the molecular model that the hydrogen has a softening effect on the flow stress here in both cases. However, in both cases that we found the insensitivity of the hydrogen concentration, especially in the molecular simulation, we can see that the three concentrations of hydrogen, but they have similar behavior. We are thinking that the reason can be that the hydrogen atom concentration is already high. So further increase the concentration won't really influence the behavior. And that also confirms that the plasticity actually may activate non-locally, because if a homogeneous nucleation applies, they should depend on the hydrogen concentration, but we didn't find this dependence. So it could be the non-local plasticity generated. And one more word about this, in the continuum model, we use the FF and MNL, two theories to calculate the sluice drag. And FF represents a very strong binding, while that MNL is the weak binding. So this is the reason why we have a small gap between these two models. And let's further see how this flow stress evolution. And we can see here that the flow stress at the small deformation is almost identical, while at large deformation, that the hydrogen starts to have the impact on the reduction of the flow stress. And this because that at a very small deformation, that the plastic zone is really small, while that's only at the large deformation when the plastic zone is comparable with the specimen size. And then we see the influence of the hydrogen. And this also indicated very low dislocation density. It's confirmed by the analysis of dislocation density curve. Small depths, similar, while that only at the higher depths, indentation depths, that the hydrogen has induced the lower dislocation intensity. Some the animation to show the whole process, comparison of the hydrogen-free, hydrogen-charged case. And it's quite obvious that in the hydrogen-free case, we found the stacking fault formed beneath the indenter, and this serves as a strong obstacle for the dislocation motion. Well, that's in the case of the hydrogen, seems that the dislocation mobility is enhanced and easy to move to the free surface and disappear at the free surface. So we can conclude that hydrogen atoms relieve the entanglement of the dislocation network and also reduce the pile-up of the dislocation in the hydrogen-charged case. So if we compare our continuum model and with the molecular simulation, we see that we have the assumption in this continuum model that the hydrogen atom will tend to diffuse to the plastic zone and concentrate on the void surface, while that in the simulation, molecular simulation, it's more dispersively distributed hydrogen atoms. And we are thinking that probably we should run both Monte Carlo simulation and molecular dynamics. That may help to solve this problem. And also there is a computation between the dislocation velocity and hydrogen diffusivity. It's in both cases. We don't have good understanding, and maybe you can help. And a continuum model doesn't really contain a term to represent the dislocation avalanche. So we cannot predict this certain job of the one during the dislocation emission and the movement in the continuum model. My conclusion is that this continuum model is a really crude model. We need a lot of refinement, but still it's possible to predict the indentation behavior. And hydrogen atoms decrease the probability of the piling up of dislocations. So the softening of the flow stress is mainly due to the reduction of the dislocation density. Yeah, here is my collaborator and funding resources. Thank you for your attention.